If we're going to try to add two rational expressions that initially have different denominators, we're going to need to find a common denominator. Now, when we're finding a common denominator for numbers, there are all sorts of shortcuts we can take. And if we find a common denominator, but it's not the smallest possible common denominator, it's not really a big deal. When we're working with polynomials, there are fewer shortcuts available. And also, it's really easy to get a polynomial that's so big we really can't work with it in a nice way. So it's important to prioritize actually finding the least common denominator. So how do we do this? To find the least common multiple of a pair of polynomials or a group of polynomials, we factor all of the denominators, and then we build the least common multiple to have all the factors that appear in any denominator. And if a factor appears with different powers, we take the highest power. The goal is that we have the smallest possible polynomial, so that's lowest degree, smallest coefficients, that is still a multiple of each of the polynomials. This is really similar to the way that we built the greatest common factor, except for the greatest common factor, we only took factors that appeared in all of our monomials or polynomials, and we took the lowest power. The greatest common factor has to go into each polynomial. Each polynomial has to go into the least common multiple. So we can think of them in this kind of hierarchy. The greatest common factor is, in a sense, underneath everything. The least common multiple is, in a sense, above everything. So let's see an example first with monomials, because monomials come automatically factored. Say we want to find the least common multiple of 3x squared y, 2x to the fifth z, and 9xy to the third, which I'm going to rewrite 9 as 3 squared, xy to the third, right? 3 times 3, that's the prime factorization of 9. The advantage of doing it that way is that now I can treat the prime numbers 2 and 3 exactly the same way that I treat my variables. So, looking at the numbers first. In my least common multiple, I'm going to need a 2 and 2 factors of 3. So I'll need a 2 times a 3 squared. Okay, that's not too bad. Now I'm going to go through the variables. I'm going to look at the x's. X is a factor of each of my monomials, and the highest power of x that appears is x to the fifth. So my least common multiple needs to have an x to the fifth. Okay, so that's my x's. I'm going to put a little check mark over my x's so that I know that I've dealt with them. Next, I'm going to look at my y's. I only have a factor of y in 2 of my monomials. If I was talking about the greatest common factor, that would mean there are no y's, because the greatest common factor needs to go into everything. But everything needs to go into the least common multiple. So if I've got a y in any of my monomials, I need a y in the LCM. So the highest power of y that I have is y to the third. That's what I have in my LCM. Putting a little check mark over my y's, so I know that I've dealt with them. So I've dealt with x's and y's. I still have a z sitting there. So now I'm going to deal with my z's. I only have a factor of z in one monomial. It's just z to the first. So I just need a z in my LCM. And that's it. I could multiply out my numbers. So I have 18 x to the 5th, y to the 3rd, z. But there's nothing else I can do with them. Notice that that actually is a multiple of each of my monomials. Right, I won't usually write this. That's 6 x to the 3rd, y squared z multiplied by 3x squared y. It's 9 y to the 3rd multiplied by 2x to the 5th z. It's 2x to the 4th z multiplied by 9xy to the 3rd. So we can actually get that 18x to the 5th y to the 3rd z by multiplying each of the given monomials by something. So that really is a common multiple. Okay, so here we did monomials. The advantage of monomials is they come automatically factored. If we want to find the least common multiple of a list of polynomials, as in this next example, we're going to have to factor them. So here we have a list of 3 polynomials, and we want to find their least common multiple. I'm going to start by factoring the greatest common factor. That's 3 times 2x squared minus 3x minus 2. So this trinomial, quadratic, leading coefficient not 1, I'm going to use the AC method. So I've got 2x squared and minus 2. My AC is negative 4. My B is negative 3. I think I'm going to split up that middle term as negative 4x plus 1x. And then in my first row, I'll have a 2x. First column, I'll have an x, a negative 2, a 1. 1 times negative 2 is negative 2. So my first polynomial factors as a 3 times an x minus 2 times a 2x plus 1. Okay, next polynomial. I've got 3x to the 4th minus 12x to the 3rd plus 12x squared. I think I can factor out a 3x squared, and then I'll have an x squared minus 4x plus 4. Oh, hey, I recognize that. That's a perfect square. That's x minus 2 all squared, right? X squared, 2 squared, negative 2 times x. So I'll have 3x squared times x minus 2 squared. Okay, cool. Then this last polynomial, I've got 2x to the 4th plus x to the 3rd minus 8x squared minus 4x. I think I can factor out a common factor of x. And then I'll have 2x to the 3rd plus x squared minus 8x minus 4. And now I have 4 terms, so I'm going to try to factor by grouping. 2x to the 3rd plus x squared minus 8x minus 4. My first row, I think I have a common factor of x squared, which I need to multiply by 2x to get 2x to the 3rd. I need to multiply it by 1 to get x squared. 2x times negative 4 is negative 8x. And then negative 4 times 1 is negative 4. So now I have x times x squared minus 4 times 2x plus 1. And then x squared minus 4, that's a difference of squares. So I have x times x minus 2 times x plus 2 times 2x plus 1. Okay, so now I've fully factored each of my polynomials. Now I can go through and find my least common multiple. So I'm going to look at numeric factors first. It looks like I have a factor of 3, 3, and no numeric factor in the third one. So the least common multiple of those is going to be a 3. Next, I'm going to look at monomial factors of x. Nothing in the first one, x squared in the second, just x in the third. The highest power of x is x squared. Okay, next I'm going to look at binomial factors. And I'm just going to go through in the order that I see them. So I see an x minus 2 in my first polynomial. So I'm going to go through and look for x minus 2 in the other two. I see an x minus 2 squared in my second polynomial, and just an x minus 2 in the third one. So x minus 2 appears. The highest power with which it appears is squared. So in my LCM, I'll have an x minus 2 squared. Okay, next binomial factor. I see a 2x plus 1 in my first polynomial. I don't see anything in my second. In fact, all the factors in my second polynomial have been dealt with. So I don't need to really look at that anymore. I do see a 2x plus 1 in my third polynomial. So 2x plus 1 appears. It only ever appears as 2x plus 1 to the first power. So I'll just have one copy of 2x plus 1 in my least common multiple. Okay, so now all the factors in my first polynomial have been dealt with. All the factors in my second polynomial have been dealt with. All that's left is that factor of x plus 2 in my third polynomial. So x plus 2 only appears the once. It's only to the first power, so that needs to go into my LCM. I'll put in a factor of x plus 2, and now I've got all of the factors from my third polynomial. That is the least common multiple of these three polynomials. And if at all possible, I very much want to avoid multiplying that out. I'm going to leave that least common multiple in factored form, unless I really need it multiplied out for some specific purpose.